have a multiplicative set and an ideal that misses it, you can grow that ideal to a prime ideal, maximal with respect to missing that set. And multiplicative sets are also important because if you think about the rules of adding fractions in the old days, how do you add two rational numbers, for example? You need denominators to be closed under multiplication. So I've got this calculus example. Let's theorem. Let's suppose that R is commutative and suppose we have a collection of prime ideals. Then the set this set right here is multiplicable closed. And in fact, more than that, there's an important theorem we're going to get to about this. Well, let me point out if A and B are elements of S. So what does that mean? That means that that means for every A and B that's in the set, that means that in particular A and B are not in PI, right? So A and B is not in PI because PI is prime. And prime is very important, right? Because remember, what makes it prime is if A times B is in there, then it must contain either A or B. Since these are prime ideals, and that's central to this, this is actually multiplicably. This is actually a multiplicably closed set. And in fact, this is the most important way to build multiplicably closed sets is as a complement of prime ideals or a union of prime ideals. Definition. Let S and R be a set. We will assume that or often when you see this definition, it's assumed that it's a multiplicable closed set. But if you look at the definition, there's no real reason why you have to assume that. We say S is saturated if so in other words, what it means to be a saturated set is it contains all of its divisors, right? Let me point out that if you have any set that is saturated, if it's not empty, then it has to contain, and the ring has an identity, then it has to contain one. Because if there's an element A in the set, then A times 1 is in the set, and it has to pick up that divisor 1. Right? So in particular, if you have a saturated set and you have a ring of identity, a saturated set must contain all the units of R. And here's the theorem of promise. Let's suppose that let's suppose that S is a set not containing zero. And you can assume that R is commutative, even with identity, although that's not really necessary. Then this set multiplicably closed. So it's got the property that is multiplicably closed and it's saturated as per previous definition, if and only if S is the complement of a union of prime matrices. I don't mean generated by, I mean just literally a set theoretic union of prime matrices. This is actually incredibly important because notice that if you want to talk about fractions, so before I prove this, let me take a little aside from the example here. Notice that the non-zero multiples of 6 in the integers is certainly a multiplicably closed set because the product of two elements that are multiples of 6 is a multiple of 6, and since the integer is an integral domain, it's impossible for two non-zero multiples of 6 to be 0. Now, if you're to look at fractions, notice that this, of course, forms a ring as well, right? But notice that you get other things in there. Notice that notice that you have A over 6K plus B over 6M. This is, well, I won't even bother simplifying things here. Actually, let me write it this way for emphasis. This is 6MA plus 6KB. And you can cancel out 6 if you want, but you notice the denominator is still multiple of 6. And this forms a ring. But notice everybody agree with this? But 6 is 3 times 2, and 1/2. So I should expect that 2 should be a denominator as well. And notice that 2 is in the saturation of the set, right? If you look at the non-zero multiples of 6, right? If you look at the non-zero multiples of 6, then what you get is a multiplicative set. This is not saturated because there are certain divisors that aren't there. 1 is not there, 2 is not there, 3 is not there, and so forth and so on. So if you look at the smallest multiplicatively closed saturated set that contains this, anyway, guess what it is? What's the smallest multiplicatively closed saturated set that contains all the non-zero multiples of 6? Well, you've got to have all the multiples of 6 in there. But to be saturated, you got to pick up 2 and 3 and 1, right? And so basically what you have is this is the set of all things. It's everything that looks like this. Everybody okay with this? So let me come full circle on this theorem here. Everybody agree with that? Because once you get two in there, it's got to be multiplicably close. So you got to get all powers of two and so forth and so on. Now let me come full circle on this theorem that we're fixing to prove. Notice this is the union of the ideal generated by P, where P is prime and P is greater than or equal to 5. Right? Because notice that if you have any prime 5 or larger, it does not divide anything in here, right? So it doesn't overlap the set at all. And this actually is true in general. That is, if you have any saturated multiplicably close set, it's a complement of a union of primes. Complement of a union of primes with multiplicably close and 5, 5, 1. I show that that's a explain why that's a multiplicably close set and saturate. In fact, for the saturated part, you don't need prime at all. All you need is ideal, right? A, B is in R minus some union of prime ideals. Suppose A is not in suppose A is not in the complement of this union of prime ideals, then A is in PI for some I, right? Therefore, AB is in PI. Because A and B was supposed to be in complement always. Notice that for this part of the proof, I didn't need that P was prime. All I needed was it's an ideal. The prime part is what you need for multiplicably. So if you have a complement of a union of primes, the prime descriptor is what you need for multiplicably close. Any ideal will do for saturation. The other direction is the interesting one. Now suppose suppose S is saturated multiple close. Basically, our goal here is to show that it is the union of a bunch of prime ideals. So let's suppose that X is in the complement of S. Therefore, the ideal of X, the ideal generated by X, intersect S is empty. Because if Rx is in S, this implies X is in S by saturation. So if X is not in S, that is X is in the complement of S, then that means that this ideal overlapping with S is empty. And maybe you smell what the rock's cooking now, because what do you know about any ideal? And this is a multiplicative set. Sprinkle some fertilizer, and you can grow that to a prime ideal. Expand the ideal generated by X to we'll call it a piece of X, such that X is contained X. Intersect X is empty. Okay. Now to finish this off, let me point out that in X and C, X is contained in X such that X intersects X. So that is X is contained in S complement. Notice that the union X and S complement PX is contained in S, because every one of these PX there we go. Because every one of these PX's is contained in S complement. And of course, we get the other containment because, of course, everything in S complement is contained in this PX by definition. So and there you have it. You could write the complement of S as a union of prime ideals. Okay. Any questions? Okay. So now we've talked a little bit about multiple sets, and this theorem is a very important takeaway that any saturated multiplicably closed set, it can be characterized by being a complement of a union of some collection of prime ideals. You know, it's fun just to play around in the integers, and it's kind of fascinating how this all works out. But now, let's show what multiplicative sets can do for us. It helps us build new rings from old in the following sense. So I am going to introduce this thing now called localization. And it's going to be more familiar in the integral domains case, right? Because it's sort of like looking at fractions. But this process can be constructed for rings with zero divisors, a lot more general than integral domains, rings without identity as well. And so we're going to do a general construction, which will collapse to something much more easier and familiar in some nice cases. Or a multiplicably closed set. Technically, I'm not assuming here that zero may be an S, although that's kind of it just turns things into silliness. And I'm not assuming it's saturated yet either. The relation on, okay, so take the Cartesian product of R and S as a set, and we're going to sort of turn this into a ring. Okay, I want to put a relation on this set first by telling you when two elements are the quote same thing. This is analogous to, like, well, for most of you guys, by third grade, I went to high school or I went to school in Tennessee, so it was like 8th grade, where we like reduce fractions and such, right? 4/8, 3/6, 5/10, they're all 1/2, right? I mean, that's probably what your teacher in grade school smack you on the hand with a ruler if you didn't get it all the way down to 1/2, right? But when you talk about a fraction, and they don't really talk about this to grade school people, but really what you're talking about when you talk about a fraction is an equivalence class. because there's many ways to represent fraction. It's the same kind of thing going on here. We're going to talk about equivalence classes. This is the notation I use in the car, but you might think of this in the back of your head as R over S, the fraction, numerator, denominator. Now, I'm going to say, what am I going to demand for these two to be equal? One thing that I think to myself is, hey, I know that like 3/6 and 5/10 were the same thing. One thing that I could have done is reduced them and say, hey, I've got the same thing here, but that's not really a well-defined process. How can you tell? You guys remember back in grade school, how do you tell when two fractions are the same? You check their cross multiples, right? I'll remember that. So 30, 30, so these two fractions are the same. That's what I've got going on here. Sort of. I want RS prime minus R prime S 0. That's sort of cross multiples, but actually that's not really quite good enough in our situation. We've got to generalize a little bit because of the possibility of zero divisors. So we were going to say this is true if and only if, almost this, but not quite, there exists a T and S such that P times S. So this is almost like the cross multiple being 0. It's not quite good enough because I may be able to extract 0 out of this multiplicative set S. And you will see actually from the proof why this condition is needed. Let me finish the statement. So this thing is an equivalence relation. And so what my setup is I am going to do just like we do in fractions. This is an equivalence relation, so I'm going to look at equivalence classes here. That's the same thing as taking like 1/2 and tying it all together with 3/6 and 5/10 and all that sort of business. So, proof. This is certainly true because RS minus RS is already 0, right? And so just to make this technically right, you could put another S there, but it doesn't matter because the RS minus RS is already 0. Equivalence relations have to be symmetric. So if RS and T RS prime minus R prime S 0. I did that right. For some TNS. So notice that it's also the case that T times R plus RS prime. So okay, so far that's kind of a yawner. The fact that it's reflexive and symmetric is not too difficult. The interesting part is the transitivity. And this one's, I'm going to check my notes on this one for sure. So the transitive case is the most interesting. And you will see why we do need that condition there. Suppose and let's say ABC is an S or such that it's A, B, and YB is ZC. Now, of course, for the transitivity, I need to show that XA is related to ZC. So there exists ST and S. Let's see, S times XB minus YA, 0, and T times YZ minus CB, YC minus BZ. Okay, good. So what I want to do now is let's know CT and AS because it's a multiplicative set, and C, T, A, and S are all elements of S. So those two things are in there. And what I want to do is I want to multiply the first equation by CT and the second by AS. So I'm going to hit this one by CT and one by AS to get so I get the first one, SCTXB. See, all those players are here. I guess I put them in order for a certain reason. I'm, of course, taking advantage of commutativity quite a bit. Minus SYI. And the second equation, if I multiply it out, is TY. One. And TZBAS. Now notice tie-cast, gotta love commutativity. These two are the same. So when you add them up, I get SCTXB minus TZBAS 0. What I'm supposed to do for the next C here, I need an STB. So I get STB XC minus ZA 0. And of course, STB is in S. So that's a big fat thing in S. And so what do we get? We get so it's equivalent. Everybody, or any questions? So here is the big theorem on localizations. So now I've got this equivalence relation. I sort of think of these as sort of fractions. First coordinate numerator, second denominator. But in some situations, it's kind of better to write it in the way we have. Theorem. Let R be commutative and S and R a multiplicably closed the set inverse R, and sometimes it's written RS. So those are two notations you see. And there's a worse one we'll see later, which is the set equivalence classes of R cross S under the relation from 5, 5, 4. Forms easy to bring. Under the following operations. Here I'm going to write R over S for the equivalence class. I'm going to write R over S just as for the equivalence class R over S, so it looks like more familiar fractions. Just remember we've got that plenty equivalence relation here. And here's the way it works. R1 over S1, R2 over S2, R1 S2, R2 S1 over S1 S2. Here S1 S2 and S and R1 R2 and R. And multiplication is easier. R1 over S1 times R2 over S2 is the product of R1 R2 over the product S1 S2. Additionally, R is not the zero ring. Otherwise, it's silly. If R is not the zero ring, and also has no non-zero zero divisors, and zero is not an S, and RS is an integral domain. Also, if R is not zero and no non-zero zero divisors, and here's a special case. What if R is not the zero ring? So what if R has no non-zero zero divisors? And what if you take S to be every non-zero element of R? Because R has no zero divisors, non-zero zero divisors, the non-zero elements of S form a multiplicably closed set because you can't multiply two things and get zero, right? So here we go. And RS is let me go through a couple of details on this. multiplication and addition will so let's just do multiplication. I'll leave addition as suppose R1 over S1 is R1 prime over S1 prime, and R2 over S2 is R2 prime over S2 prime. That is to say, basically those things are represented as the same equivalence lines, right? So, what does that mean? S, P, and S. So, S, R1, S1 prime minus R1 prime, S1, 0, and T, R2, S2 prime minus R2 prime, S2. Now our burden is to show. So we need to show that R1, R2 over S1, S2 is equal to R1 prime, R2 prime over S1 prime, S2 prime. Agree? Need to show that, you know, if you pick these two, for your representatives, multiply them, and I pick these two, we need to be getting the same answer. Right? And this is equivalent to showing there exists Z and S such that Z times R1, R2, S1 prime, S2 prime minus R1 prime, R2 prime, S1, S2 is equal to 0. And so it looks to me like this is going to be another sort of multiplying things out here. So how will we do that? Well, notice that we have S R1 S1 prime minus S R1 prime S1 equals 0. Multiplying this first one out, and T R2 S2 prime minus T R2 prime S2 is 0. And what we need right here is ZR1 R2 S1 prime S2 prime minus C R1 prime R2 prime S1 S2 0. Now it's tempting. Well, I guess what we could do is we could multiply this by Right, so how do we get this well defined? And if we multiply, well, let's just say I get to multiply these two. So I get ST R1, R2, S1 prime, S2 prime, and then I get this mess in the middle. I get minus ST R1, R2 prime, S1 prime, S2 minus ST R1 prime, R2, S1, S2 prime. And then I get plus ST R1, R2, R1 prime, R2 prime, S1, S2, 0. Right. And that's not quite what we want here. So how do we adjust this, right? So I guess probably what I need to do here is, this is probably the wrong tack. Here's something that'll work better. Here's what I want to do. Let's multiply this one by, I guess, R1, S2 prime. I'm not R1, R2, S2 prime. And that'll get me sort of what I want here. And I probably want a T too, right? And so that'll give me an ST R1, R2, S1 prime, S2. And here, I think that's a good call. I guess R1, S1 prime. Like that. Let's see what happens. So out of this one, I get ST R1, R2, S1 prime, S2 prime, minus ST R1 prime, R2, S1, S2 prime, 0. And from this one, I get ST R1, R2, S1 prime, S2 prime. Well, actually, I wasn't thinking properly about this, because I think what I need to do is I need to make this one match up. So let's try again. Let's go on this one, S R1 prime, S1. Yeah, that makes more sense. So this one gives me ST R1 prime, R2, S1, S2 prime, minus ST R1 prime, R2 prime, S1, S2. And that better work. We'll see. ST R1 prime, R2, S. Righteous. So if you add these up, you get ST times R1, R2, S1 prime, minus R1 prime, R2 prime, S1. And so multiplication. And I'm glad that we kind of slogged through that computation, because that really shows you why you need that condition. Yeah. Let me point out a couple other things. Basically, the fact that this is a ring, it's certainly closed under addition and multiplication because of the way we set it up. It's tedious that you you can show that things are associative and it distributes. Let me point out for all S in S, 0S is 0 element. Also check this. Also, S over S functions as 1. In this new ring. That's why you may have wondered about that, because I didn't say the theorem of the ring has identity, but in the localization, I say if R is not 0, there's no non-zero divisors, then this is an integral domain. And what's this business about the 0 divisors? Sort of notice that R over S if and only if there exists T in S such that T times so let me point out if R has no 0 divisors, then T equals 0 or this is to be 0, right? And if 0 is not in S, only matter can occur. Right? Because T can't be 0 if 0 is not in S. Sorry. If 0 is not in S, then this T can't be 0. So if you've got no non-zero divisors and the multiplicative set doesn't contain 0, then there you go. Okay, any questions? Okay, so I think I've got time to write down one more theorem. And next time we'll look at how localization behaves with ideals. The first homomorphisms of theorem. Let's suppose that S is a multiplicably closed subset of R. Closed. And T with 1. T is with 1. If F more T is a homomorphism. This is a homomorphism brings with F contained in unit T, all S and S. So in other words, it takes every denominator to a unit in S, right? That's the condition there. Then there exists a unique homomorphism. We'll say F bar, the more localized F in the T, such that oh, well, I need to set a word because I completely freaked out. I'll give you, I've got something undefined I'll have to say next time. Such that F bar P of S equals F. And RS is determined up to Isomorphism. And I'll go into this in more depth next time, but basically, let me tell you what P of S is. We talked about this last time. P of S is basically a homomorphism from R into RS. How does this work? You know, I'm tempted to write R over 1, but nobody said that there's 1 in here. So this is almost like a cheat. S is some fixed, so this you've got some fixed S in the multiplicative set. For this fixed S, you have this correspondence that gives a homomorphism. Okay, any questions on that? We'll dig deeper into this next time. How about out there? Any questions? All right. Well, y'all have a good one, and we will catch you on the flip side.